aujourd'hui la session de GTM, Ludovic, Rifford, de l'Université de Nice, qui nous parlera sur la conjecture de Sard Conjecture en géométrie sous-Riemannienne. Merci beaucoup pour l'invitation. Donc, je vais effectivement vous parler de la conjecture de Sard minimale en géométrie sous-Riemannienne. Donc, en fait, je vais parler en français ou en anglais? En anglais, ok. So I'm going to tell you about the Sard conjecture, the minimal Sard conjecture in sub-Riemannian geometry. And so this is a work in collaboration with André Belotto and Adam Parusinski. André Belotto is here in Paris, at Paris 7, you probably know him, and Adam Parusinski is in my department in Nice. So let me write the title. So on the Sard conjecture, so I know that I'm speaking in a seminar of geometry and model theory, so I guess you are not very familiar with sub-Riemannian geometry, in particular with the Sard conjecture. So I'm going to recall the setting, and then to state one or two results, and then to give you an idea of the proof. Okay. So let me write complete the title on the minimal Sard conjecture in sub-Riemannian geometry.
So the Sard is the same one from Sard's theorem? Or?
Yes. And so so in fact, sub-Riemannian geometry is kind of expansion of classical Riemannian geometry, where that gives rise to much richer metric spaces. And in this setting of sub-Riemannian geometry, we have plenty of open problems, and the main ones are what we call the regularity of minimizer in sub-Riemannian geometry, and the other one is the Sard conjecture. In fact, I gave a Bobak seminar on which were more focused on the regularity of minimizer 10 years ago, I think. And you were there, you remember? Yeah? No?
I was in many such lectures, so I don't know.
So there was one, and you asked a very good question, very relevant question. You don't remember?
Maybe.
Okay, so today I would like to speak about the Sard conjecture. And so it is named after Sard, but in fact it's not the conjecture that is due to Sard. So maybe we should change the name of this conjecture. It could be called the Mongan-Zitomirski conjecture. I think it appeared in a paper I read these two authors. So let me recall the setting of sub-Riemannian geometry. So I'm going to consider M a smooth manifold.
So this paper was after or before Sard? No.
What?
You said there are two people who proposed.
Yeah, so Sard, it was in the early 20th century, Sard. Arthur Sard in the 1940s.
Yes.
He proved the classical Sard theorem, and the paper by Zitomirski and Montgomery was probably in the 90s.
So it didn't have to do with Sard?
Yeah, you will see. It has to do with Sard. There is a strong connection with the classical Sard theorem, and that's why we call it Sard conjecture. We should maybe call it Sard problem. You will see. I will explain. Okay, so we consider a smooth manifold of dimension n, and say it is connected. Okay. I need, in order to define the sub-Riemannian structure, in fact, I won't precisely define the sub-Riemannian structure today, but we only speak about bracket generating distribution. So I need to consider on M what we call the bracket generating distribution of rank M, which is less than n. Okay, so you know what is a distribution. Okay, it is a subbundle of a tangent bundle. At every point, the delta is parameterized by m vector fields. Okay, so maybe locally you have open sets where you have this. Okay, in charts locally you can write this. And so saying that it is bracket generating means that you require the distribution, you require that the Lie algebra, which is generated by the vector fields, so it gives you a Lie subalgebra of vector fields. If you evaluate it at some point x,
then you can recover the tangent space of M at X.
Ah, okay. So everything is infinity.
Yes. Thank you. Everything is C infinity. It is smooth, and the vector fields, the distribution is smooth. Okay. And so now you consider a path valued in M. Okay. You assume that it is W12, which means that it is continuous, absolutely continuous. It has almost everywhere a derivative, and you assume that this derivative is in L2 with respect to some metric you take on M. Okay? And yet then you say that it is horizontal with respect to the distribution you have given if for almost every time where it is differentiable, you have that the velocity of this path is in the distribution.
Ah, okay. Almost everywhere.
Almost everywhere. Since it is only W12, a priori you don't know if it has the derivative everywhere, so you require this only where at the point where it is differentiable. Okay? So, examples. So the first example you can have in mind is the case where M is equal to N. Then you see that in this case, so you have that the distribution at every point has dimension N, and so it is equal to the tangent space. And so it means that in fact, being horizontal is not a constraint. Any path which is W12 is horizontal. Okay? In sub-Riemannian geometry, the objective, the main purpose is to see how you can connect two different points in the manifold by an horizontal path. Okay? And then you will, I'm going to state a result saying that under this assumption you can do it, and then you will equip the manifold or the distribution with a metric. And then it will allow you to give the sense for the length of an horizontal path between two points. Then when you have the notion of length, you can define what is a minimizing path between two points. This is the path with minimal length between these two points. Then you can define a distance function. You can do metric geometry. And you can also study how are the paths that minimize the length. And so you can study geodesics. And then you can study the geodesic flow, etc. Okay? So, proceeding in this way, you can define a geometry and see and study the properties of this geometry in terms of the distribution of the metric and the topology of the manifold. Okay?
If you're interested in length, maybe it should be more natural to, you had the L2 condition on the path, but it's maybe more natural to have L1 because when you consider the length, it's like the interval of the
in fact, it's the same because if you reparameterize the length, you can define it for L1, but you would like to have geodesic with constant speed.
Yes.
And so minimizing the L1 norm or the L2 norm will be equivalent, in fact.
Ah, okay. So it's the same.
It's the same, in fact.
Essentially the same.
And since L2 is Hilbert space, it's more convenient to work with it rather than L1 norm. Okay? Okay, so as I said, so the case n equal to n is the case where being horizontal is not a constraint. And so it's the case where you will study the path connecting two points with minimal length, and so it's exactly Riemannian geometry. Okay? So I won't speak about this case. It's not interesting to me. So from now on, I'm assuming that n is strictly less than n. Okay? Okay, so let us continue. So we have a theorem. I will come back to other examples later. Theorem. So let me define a notation, introduce a notation. So I fix x in M, and I denote by omega x, the set of horizontal paths starting at x. Okay, so I could consider this set and show that it is what we call an Hilbertian manifold. Okay? It is a set of infinite dimension, and I couldn't define charts in order to see it as an Hilbertian manifold. I won't do it. To be simpler, I'm going to consider a family of vector fields that generate the distribution, and I would like to show you how I can reach, parameterize all the paths in this set. Okay, it will be convenient for the sequence. So let us consider a family, a finite family of vector fields. So smooth, of course. Let's say x1 to x scale, such that for every so let's say that the x which is fixed, it has a bar, so that it cannot move. So that for every x in M, we have that delta of x is equal to the span of x1 x. Due to topological constraints we may have on the manifold, we can certainly not take k equal to M. We can certainly not parameterize globally the distribution by exactly M vector field where M is the rank of the distribution. However, you can show that you can find a finite number k, which is something like M times M minus 1 or M plus 1, so that you can write this. Okay? So at every point, I have this equality, and of course, since k is larger than M, the vector fields are not linearly independent. Okay? There is an eraser somewhere. I guess. And now I can define this mapping, and so you will see how Sard appears in this setting. So I define the mapping, which is called the input-output map, or the endpoint map, which is the following. So I will tell you that x bar is fixed. I need to add an assumption, otherwise I will have a question about this. So let's assume that the flow of each vector field is globally defined. Okay. So for instance, you can consider on M a complete Riemannian metric and assume that the vector fields here are bounded globally. Okay. And so you define this mapping. Okay, so I take something in L2, I do it in Lk. I call it U. In general, we call it a control. I was told that, in fact, in Russian, I don't speak Russian, control, the name which is used to say control, start with U. I don't know which one. But that's the reason why we call it U, because you know that André did a lot of things in control theory, and so yeah, they use the letter U. Okay? And so you send it to what?
What relation of U to Parusinski?
Parusinski, he made some works on the optimal control.
But why the notation?
No, some Russian guys worked on it was not sub-Riemannian geometry at the time. They did some works in optimal control, yes. And they used the letter U to denote a control.
Okay.
And we kept this tradition, call it U. Okay, and so you take a control U and you send it to this point in M, which is defined as follows. In fact, gamma U is an horizontal path such that it is solution of this equation. So it's an autonomous ODE. With starting point x or x bar. Okay? So when you take control in L2, so as I said, I assume that the solution to this Cauchy problem is well defined over the interval 0, 1.
Okay, so it's not enough, you can integrate each of them, you want?
Yes, that's why I said that I need them, for instance, to be bounded globally.
Okay, so if they are all bounded with the Riemannian,
if they are all bounded with respect to some complete Riemannian metric, it's okay. Okay?
Okay.
So you take a control U in L2, you write this Cauchy problem, and so it gives you a a path which is in W12 because U is in L2. The vector fields are bounded. Okay. This path, almost everywhere, you can write its derivative as a linear combination of the xi. So it is valued in the distribution. And by construction, it starts at x bar. So in this way, by doing this, you recover all the paths which are in this set gamma x. Omega x. X bar, I should say. Okay? Well, as you can see, since k is larger than m, we don't have unicity. Maybe I should specify that, in fact, when you take an horizontal path in this set, you can see it as a gamma u for some u.
But you have to go the other way. You need to write something in N2 as a linear combination like this. So you need that the generators are not too small. That is, that locally you can choose an orthonormal basis using or something like this. Because otherwise, like if there is a k. Yes, but the generator somehow decay very fast, and then you use coefficient L2, you get only small things.
You can do
all L2 things. Not all L2 things, I think.
No. So let me say it again. If you take a path in W12 locally among this family of vector fields, there are m of them, which gives you a linearly dependent family of vector fields. Okay? And so on this maybe piece of interval, you can find a control U. Okay? And so what happens is that since k is probably much larger than m, you don't have uniqueness. If you take an horizontal path, there are several possible u that gives you that the path that you consider is equal to gamma u. But indeed, there is at least one. You have instance, but unique. Okay? So if we were in the case where k is equal to m, I would obtain an exact parametrization of the path in this set by L2. Okay? But you see, it is not the case. Okay? So the very important point to me is to be able to parameterize in a non-unique way, in a non-univoc way, all the path in this set. Okay? So now I can state the result I wanted to state, proposition. So this mapping, so as I said, is called the endpoint mapping. So it is defined on L2, which is an infinite dimensional space. It is valued in M. Okay? And you can show that it has the same regularity as the family of vector fields. So it is smooth. Okay? Proposition. This mapping is open. Okay? So you can show that if you take an open set in L2, if you take the image of this open set by this mapping, you obtain something which is open. In particular, remark, if you take u equals 0, the path which is associated with u equals 0 is the constant path equal to x bar. If I take a small ball in L2 centered at u equals 0, it is a small open ball, its image will be an open set in M. So its image will be a neighborhood of 0. So it tells you that there is a small neighborhood of 0 such that every point in this neighborhood can be connected to x bar along the horizontal path. Okay? So the fact that this mapping is open is due to the fact that the distribution is bracket generating. Okay? If, for instance, you were in the case where the distribution is, as the opposite say, it is involutive, then you would have to remain in a leaf of foliation. So you would not be able to reach a small neighborhood of a point. Okay? And so, by using this kind of argument, you can show the famous Shor-Hassevsky theorem, which tell you that for any x and y in M, there is gamma horizontal such that gamma equal starts gamma of 0 equal x and gamma of 1 equal 1.
So, and the other one?
Rashevsky.
With 2 eyes.
Yes, it's a question of terminology. Joe Rashevsky in the 30s, I think it's 38 or 37. Okay, so you remember at the beginning I said that M is connected, and so using this and using this you prove easily that if you are given 2 points in M, you can connect them along an horizontal.
This y, what did you like? Y?
There is gamma, an horizontal path which connects x to y. Okay?
Can you take it to be piecewise smooth?
Yes, I could take it to be smooth. Smooth. C'est infinitive, yeah. So I can take it piecewise smooth. I can take it analytic. Algebraic. You are in Rn, for instance. Yes.
I'm sorry, a little bit just by curiosity. Is it always so? It's not possible if the variety is a manifold is of dimension greater than one-dimensional delta will never be bracket generating. But is it always possible to have a two-dimensional delta bracket generating? Or?
Yes.
Yes.
If you are on a manifold of any dimension, so at least 3. If you have a distribution of rank 2, so there is a topological condition because you need the normal to the distribution to exist. You need to have a line field on the manifold. Okay. So there are some restrictions. If you have a 2-dimensional distribution, you perturb it, it will be bracket generated. It's an open condition which is dense in the set of rank M distribution. Okay, so let's go back to some examples. So the first example of sub-Riemannian structure. So here I'm just considering the distribution. The sub-Riemannian structure is given by a distribution together with a metric. Here I don't need to consider a metric. So when I say in fact sub-Riemannian structure, I have in mind to have also a metric, but we don't need it today. Okay, so in R3, let's say with coordinate x1, x2, x3, and so I take the distribution which is defined by the 2 vector field x1, x2 with x1 equal to x1, constant vector field, x2 equal to x2 plus x1 x3. Okay? So you can check that the Lie bracket of x1, x2 is x3. So in fact, at every point you have that x1, x2, and Lie bracket of x1, x2 generate the tangent space R3. Okay, and you can also check the following. So assume that x bar is equal to 0. Okay, so I take a point which is 0, 0, 0. Okay, and let's take control. So let U in L2. Okay, and so let's call it U bar. Okay, and so gamma U will be solution of this. Gamma U bar will be solution. So I'm going to write it like this. Gamma U bar of 1, it will be, so you have to integrate this Cauchy problem starting at x bar equals 0. So I write the solution, which is very easy because you have a system which is very simple. So you have 3 coordinates. So the 2 first variables will be given by the integration of U1 and U2. And the third one will be this. Now, do you agree with me? Yes? I just integrated this system, okay? And now I would like to just tell you what happens when we do a small perturbation of U bar. Let's say it's the first order of perturbation. And so when you will compute this, you will have, you can write kind of Taylor formula, and you will have what corresponds to delta U equals 0, and then you will have first order terms in delta U. You will have this. So it's very easy for the first part because it's just this, then it is just this. Then here you have to compute, so you will have a U2 bar plus delta U2, U1 bar plus delta U1. I just keep the first order term, you have this. Okay, you have this. So here you have the delta 2, delta U2, here you have delta U1, here you have U2 bar, here you have U1 bar. And so, writing this, you can infer that in fact, if you have that the control U bar that you consider is not equal to 0 in L2, okay, there is a set of positive measures where U bar is not 0, okay? Then it will allow you to say that this is here at some point not 0, or this one is not 0. And so it will tell you that by taking, by changing, by perturbing, by considering the right values of delta Q and delta U1, you will be able to show that this mapping at U bar is a summation. Okay? So if I write it in another way, you will show that the differential of this mapping from L2 to the tangent space at the final point of this in M will be subjective, because you have something which is not 0.
Assuming that either one of them is not 0.
Yes. Let me
So here is U bar not 0.
Not 0, it means it is a function on the interval 0, 1, so it's not equal to 0, 0 in L2.
Okay, because you write something.
Ah, sorry, yes, thank you. And let me consider another example, which is, so this one is the classical Heisenberg case, what we call the Heisenberg sub-Riemannian distribution. Let me now modify it a little bit to consider the Martinet case. So let me change a little bit the vector fields, the second one in fact, by taking a square here instead of a power 1. So example 2.
Okay, so this is just an action of the two-dimensional list of algebra on the Heisenberg group. Okay.
Yeah. Yeah, you here if you write the Lie algebra, then you cover the Lie algebra, or Heisenberg Lie algebra. Okay, and so let me consider now in R3 these two vector fields. So x1 is the same, x2 is the same, it's not the same in fact, because here I replace I replace the power 1 by a power 2. The effect of this is that when we compute the Lie bracket x1, x2, before we had dx3, now you have this.
This is x1, the first derivative is x1 or x2?
X2, thank you. And so when you compute this, you have an x1 that shows up. And then in order to check that you have bracket generality, you need to compute another Lie bracket, which will be this one. So the distribution which is spanned by x1 and x2 is bracket generality. The difference is that the number of Lie brackets you need at any point to generate the tangent span is not the same. It's not the same when you are on the plane x1 equals 0. Okay? Now, if I come back to my computation, Okay, so let's take the computation made before for Heisenberg. Then you will have this. Okay, and then because of this square, the first order term will be different. Okay, so let me. So there will be a term in delta U2 times this one. So here there was a mistake. It was okay, there is this one. There is a DS missing, plus this one. Okay. Times, so the square that will give you something like this, times this, U1. U equal, for instance, this, so it is not 0. When you take this, sorry, I made a mistake. So you take U1 equals 0, U1 bar equals 0. When you do this, here you have 0. And here you have 0. Which means that in fact, when you take, so you start from 0, and you take U2, U1 equals 0, U2 equals 1. So it means that you follow the vector field dx2, because x1 is equal to 0. So you do this. Okay? And so it tells you that you cannot make perturbation at first order in order to go in the vertical direction. Because here the distribution is, let's say, horizontal, it's in x1 is 2, okay? Because the third coordinate here, which is given by the distribution, is 0. So you can easily go in the direction which are in the x1 and x2 variable, but if you want to go to the x3 direction, you cannot do it at first order. Okay? You can, in fact, say more. If you take this control, which is smooth, so it is smooth, okay, it is constant. If you take a perturbation of this control in C infinity, or even in C0, you will have, since U2 is positive, this will be close to 1 if you perturb a little bit in C0 topology. This is a square, so this term will be positive. So it means that the perturbation of this horizontal path here in C0 topology does not allow you to make x3 decrease. Okay? So that's why when I stated that the mapping is open, it's very important to start from L2. If you don't start from L2, you are not open. Okay? That's why it's very important to consider horizontal path which are in W12, not only C0 or smooth. You really need to have something much more flexibility than C0 or something like that. Okay? So it was to give you an idea of what we call a singular path. It's a path, it's a path where you cannot achieve a perturbation at first order in any direction at the final point of your path. In other words, it's a path which is associated to a control which is a critical point of the input mapping. So definition, a path, an horizontal path is called singular if there is U in L2 such that gamma equals gamma U. So let's assume that gamma is starting at x bar. Okay. So there is a control such that gamma is equal to some gamma U, and U is the critical point of the input mapping. What?
But it could be that there is another controller gives it, which is not critical.
Effectively, you should ask. You should wonder now if it may depend on the control. The answer is no. If you are singular, if there is a control U which gives you this and which is the critical point of Ex bar, then any control that gives you this will be critical. Okay. It does not depend upon the control issues, because we know that we have existence of such a control allowing to write this, but we don't have unit tests. But this definition does not depend on the choice of the control. Okay?
Okay, so you can just use the space of paths instead, the manifold instead of the control.
Exactly. You could define, as I said before, you could see this set as a set of paths, so it would be a Hilbertian manifold, and then the path is singular if it is a critical point of the mapping sending a path to its endpoint. Okay? And so now, imagine that you see Sard coming. We have a mapping. We have a notion of a critical point of this mapping that gives us a notion of singular path. Then the Sard conjecture tell you or expect that for every X bar in N, the set, and the definition, the set of endpoints of singular path as measure 0. The set of endpoints of singular path in this set, so the path starting from its bar, H le bec mesure 0 in N. In other words, the image of the set of critical points of the mapping Ex bar as the bec measure 0. This is the Sard conjecture in sub-Riemannian geometry. So as you know, the classical Sard theorem, which is a theorem which holds true in finite dimension, it tells you that the set of critical values of a sufficiently regular mapping has the bec measure 0. And so this is precisely the Sard conjecture. And the problem is that here we have a mapping which is smooth, but it is defined on L2, which is infinite dimensional space. That's the problem. There is no general Sard theorem in infinite dimension. In fact, it is false. You can construct examples of polynomial functions on L2 valued in R, whose set of critical values is an interval, for instance, or R is false in infinite dimensional Sard theorem. But still, we expect that we should have this, because this mapping is very specific. It's not any smooth mapping. Okay?
Can you replace a path connecting 2 points by another? Can you perturb a path so that it has the same endpoint and it is no longer singular?
Yes. For instance, so I can tell you a little bit about singular path. You can show that, for instance, so I'm not sure I understood your question. For instance, I said before that if you are given two points, let's say X and Y, then you can connect them by an horizontal path. In fact, if you have a set of paths which is dense in L2 or in W12, okay, then you can also connect 2 points by a path in this set of paths. For instance, the set of smooth paths is dense in L2. In W12, you can approximate any path which is in W12 by a smooth path. So in fact, you can show that you can connect 2 points by a smooth path. You could do the same with algebraic, as I said before. And in fact, you can show that the set of non-singular path is dense.
Set of
non-singular path is dense.
Non-singular path.
Yes. And so you can connect 2 points by a path which is smooth and which is non-singular.
But the pre-image image under the endpoint of a dense set. Because the map is open, the pre-image of a dense set is dense. So if you are given a dense set in the manifold, the pre-image is dense. But then this contradicts the assertion that you made about the fact that you can connect by something in a dense set. You said for any dense subset you can connect by passing the dense set. I just gave you an argument that shows it.
No, in fact, you gave me an argument saying that the pullback, the inverse image of a set which is dense.
Assuming that what you said, all what you said is correct.
Yeah.
The map, I did everything that you said.
Yeah,
the map, assuming, okay. But you said several things, so I make a contradiction assuming everything is correct. So if you have a dense set, the pullback is dense, and then you said that you can connect by a dense part. If you have 2 points, you connect them by something in a prescribed dense set. But then this cannot be true because you can take the dense set, which is the pre-image of something you can.
Maybe so. The idea is that if you can connect. If I can connect one point x to one point y by a path which is non-singular, any path which non-singular, it means that you have a mapping which gives you a local diffeomorphism up to restriction.
Yes.
So if you take a small perturbation of this path, you keep a mapping which is a small diffeomorphism, and so if you consider something which is, it will allow you to, how to say this? Maybe it was not sufficiently clear what I said, it's sufficiently precise. But the idea is that if you have maybe a subspace which is, maybe you need to have a vector space, something like this.
Okay.
You see, the idea is just what I said, to show that, for instance, if you want to have a smooth path between 2 points, you take a path which connects x to y, which is non-singular, okay? Then locally you have, as I said, a little diffeomorphism up to restriction. You can take a restriction to the set of smooth paths, and there will be a smooth path in a local neighborhood of your path, which will give you the right point, okay? That's the way you can write the proof, okay? So you need to consider at some point something which is dense, because since you have a local diffeomorphism, it means that you have some direction along which you have what you want. You need to be able to approximate this direction by smooth control, for instance. So that's where you need density. But maybe the path that you will obtain, it will be a combination of smooth things that you used where you use your density argument. So we can discuss after.